This is Trigonometry video lecture for section 1.1 on angles, degrees, and special triangles. So first we have some definitions we need to get out of the way. An angle is formed by two rays with the same endpoint. So if you can see here, we have drawn two rays. They start at 0. One extends upwards, and then the other one's shown to extend downwards. We're labeling the initial point where they start, or the common point, O. This common endpoint is called the vertex of the angle. So right here, this is the vertex. And the rays are called the sides of the angle. Now, in the figure below, the vertex of angle theta is labeled O, and A and B are points on each side of theta. And you can see A and B drawn here. Now, angle theta can also be denoted by AOB, where the second letter associated with the vertex is written between the letters associated with the points on each side. And you might have seen this sort of notation maybe in previous math classes if you took some sort of geometry or something, where you would write angle AOB, or it also could go the other way. I mean, why not? Angle BOA. But typically we won't refer to angles that way just because it involves a little bit more messy notation. We can also think of theta as having been formed by rotating the side OA about the vertex to the side OB. So you can think of rotating that side OA towards the side OB. And in this case, we would call OA the initial side of theta and OB the terminal side of theta. Now, when the rotation from the initial side to the terminal side takes place in a counterclockwise direction, the angle formed is considered a positive angle. So standard direction, for orientation is counterclockwise. If, however, the rotation is in a clockwise direction, then the angle formed is a negative angle. So here I've shown using the same initial and terminal sides. So this is the initial side. This is the terminal side. When you rotate in the counterclockwise direction, this would be measured as a positive angle. If you were to go from the same initial side to the same terminal side, but in the clockwise direction, that would be measured as a negative angle. All right, now degree measure. One way to measure the size of an angle is with degree measure. And the angle formed by rotating a ray through one complete revolution has a measure of 360 degrees, which we write 360, and then you use a little circle as a superscript to indicate that it's degrees. Make sure if you're using degrees, you don't forget to indicate it using the notation, because we have another unit of measure for angles. And if you forget the degree sign, then it means you're using the other measure, which wouldn't be right. So don't forget to write it down. Now, one complete revolution, if you spin all the way around and your initial side is the same as the terminal side, so you come all the way back, one complete revolution is 360 degrees. All right, very good. Bonus question. What if I were to go the other way, clockwise? Starting from the initial side and I go all the way around back, terminal side same as the initial side. Reverse direction would be negative 360 degrees. Nice. All right, now 1 degree is 1/360th of a full rotation. And likewise, 180 degrees is 1/2 of a full rotation. And 90 degrees is half of that, or a quarter of a rotation. And you can see below, we have drawn a 90-degree angle, which is a quarter of a full rotation, as well as a 180-degree angle, which is half of a full rotation. Now, angles that measure 90 degrees are pretty popular, and they're called right angles. probably heard that before. And angles that measure 180 degrees are called straight angles. Just think because they make a straight line. Now, angles that measure between 0 and 90 are called acute angles, while angles that measure between 90 and 180 are called obtuse angles. So if you can see here, this third angle on the top is an acute angle. I know that because it's less than 90 degrees. 90 degrees would be a right angle right here. This is less than that, so that makes it an acute angle. And then if you look at the other angle shown here in the next row, this one's an obtuse angle. How do I know that? Well, 90 degrees, the right angle, that's the reference point, would be right here, and this is larger than 90 degrees, which makes it obtuse. Now, if two angles have a sum of 90 degrees, they are called complementary angles. And we say each is the complement of the other. So for example, two angles that are complementary would be something like 30 degrees and 60 degrees. And you would say 30 degrees is the complement of a 60-degree angle, and vice versa. 60 degrees is the complement of a 30-degree angle. Also, two angles that sum up to 180 degrees are called supplementary angles. So an example of supplementary angles would be like 10 degrees and 170 degrees. They both add up to 180. Just so you don't get them jumbled up, I'm going to show you a trick someone showed me years ago. It was actually a student I used to tutor. So C stands for complementary. S stands for supplementary angles. You just need to draw one line on each letter. So the C now becomes a 9. Ooh, okay, so complementary angles add up to 90 degrees. Add a line to the S, bam, now it's an 8. So supplementary angles add up to 180 degrees. See how nice? Okay. But hopefully you'll just remember, if you're having a meltdown though, that trick should help you out. All right, now let's work on an example. It says give the complement and supplement of each angle. So to get the complement, you would do 90 degrees minus whatever angle they give you. I'll call it theta. And then to get the supplement, you would do 180 degrees minus whatever they give you. So for 40 degrees, let's get the complement of 40 degrees. So the complement would be 90 minus 40, which is 50 degrees. Notice I'm writing degrees for every single step. And the supplement would be 180 minus 40 degrees, which is 140 degrees. Nice. Okay, example B, 110 degrees. Now that might seem a little weird because complementary angles should sum up to 90. Well, that means we're going to have a negative complement. So you take 90 degrees minus 110, and that's negative 20 degrees. And the supplement would be 180 minus 110 degrees, which is 70 degrees. Okay, last one. I sort of gave you the answer already because they didn't tell us what the angle is. They just called it theta. So our answer is going to be in terms of theta. The complement would be 90 minus whatever this theta is. And the supplement would be 180 minus whatever theta is. That's it. So we can't actually find a measure because they didn't tell us what theta was. But as soon as they do, we're ready for them. Okay, now let's move on to triangles. Now there's different types of triangles and they're named according to the relative lengths of their sides or their angles. So we can classify triangles based on sides or angle measure. The first one shown here is equilateral. Equilateral is special because not only are all the sides equal in measure, and this is indicated by the tick mark or the little dash drawn through each side. So whenever that's done, that means whatever side has that tick mark is the same measure. All three sides are the same measure and all three angles are also the same measure. The next triangle is isosceles. And in an isosceles triangle, two of the sides have the same measure. So notice here, these two sides are equal in measure because they have a single dash through them or a single tick mark, but the base here is a different length and it has two tick marks through. If none of the sides have the same measure, then it is called a scalene triangle. Maybe some of this is familiar from back in the day. Now this is if we were to classify triangles based on their side lengths. We could also classify them based on their angle measure. So notice here in this first triangle, each of these three angles, I don't know what their measure is. Okay, I'm gonna assume they're all different measure. They're all less than 90 degrees. So this is an acute triangle. So in an acute triangle, all three angles are acute. The next one is an obtuse triangle. And an obtuse triangle has exactly one obtuse angle. Where is it? It's right here. It's bigger than 90 degrees. 90 degrees would be somewhere right here. You can only have one obtuse triangle, one obtuse angle in an obtuse triangle because, as we're going to talk about in just a second, all of the angles in a triangle add up to 180 degrees. So you can't have more than one that's larger than 90. You'd run out of degrees. And the last one shown here is a right triangle. We're going to be working with right triangles extensively, and right triangles have one right angle. Could a right triangle have more than one right angle? No, because two right angles would give you 180 degrees and you would have nothing left for the poor little third angle. Okay, now special triangles. Right triangles are very important to the study of geometry because in every right triangle, the longest side is called the hypotenuse, and it is always opposite the right angle. So let's go back to this picture here. This side is the hypotenuse. That's the longest one. That's opposite the right angle. Very important triangle. The other two sides are called the legs of the right triangle. It doesn't matter which is which. Here's a leg, here's a leg. Because the sum of the angles in any triangle is 180 degrees, the other two angles in a right triangle must be complementary acute angles. So they're complementary, they're going to add up to 90, and they're both acute. They're both less than 90. This leads us to the Pythagorean Theorem. So in any right triangle, only use it for right triangles, people, the square of the length of the longest side, the hypotenuse, is equal to the sum of the squares of the lengths of the other two sides, called the legs. You've probably heard it before, but it's easier just to remember the formula that is the Pythagorean Theorem. So let me draw in and indicate angle C as my right angle. And usually when we're labeling triangles or geometric shapes, you use capital letters to indicate the angles, and then the corresponding lowercase letter for the side opposite that angle. So what do I mean? If this is angle C over here, this side is going to be little baby c. And then we have angle A up top here, which means this leg is lowercase a. And then same thing, this is angle B, so this side is going to be lowercase b. And the Pythagorean theorem tells us that the square of the hypotenuse, the longest side, so c squared, is equal to the sum of the two legs squared, a squared plus b squared. All right, very good. So now let's apply it. We're going to solve for x in the right triangle. Now, they can flip around how they draw the triangles. Don't let yourself get out of sorts. Let's label where the hypotenuse is. It's right here. So this is going to be my c squared. And then here, x is equal to a, and x plus 7 is equal to b. So this is little b, and this is a. So we can go ahead and set everything up. I'm going to have c squared equals a squared plus b squared. All right, very good. Now we have to solve this quadratic equation. Now, if it's been a while since you took some algebra, you might need to refresh a little bit on solving quadratic equations. I'm going to square 13, that's 169. this is equal to x squared plus, now please be so careful when you multiply out x plus 7 and you square it, because it's not x squared plus 49. No. So x plus 7 squared means x plus 7 times x plus 7. And when you FOIL it out, notice you have x squared plus 7x plus another 7x plus 49. So this is actually x squared plus 14x plus 49. All right, good. Now from here, since we have a quadratic equation, quadratic meaning there's an x squared in the equation, not just x to the first power, x squared, you want to set it equal to 0. So I'm going to subtract 169 from both sides. And here I'm going to have 0 equals, notice these are like terms, x squared and x squared. So that's 2x squared plus 14x. And then 49 minus 169 is negative 120. Okay, now you have a couple options here to solve. You might have heard of the quadratic formula. That's great. Easier thing to do though is see if it factors, and we're going to practice factoring extensively. I right away notice I can just divide everything by 2. That'll make the equation a lot nicer to work with. So let's do that. So now I have 0 equals x squared plus 7x minus 60. So let's think here, can we factor what two numbers multiply to negative 60 and add up to positive 7? Can you think what multiplies to negative 60? 60 and 1 won't work. 2 and 30, no. Keep going through your list, and then finally you go, oh, it's 12 and negative 5. So x plus 12 times x minus 5. Then from here, we're going to use our zero product property, which means x plus 12 is 0 or x minus 5 is 0. And so x is either equal to negative 12 or 5. All right, that's it. Now there's a lot of algebra required to solve that problem. We had to factor, we had to FOIL, we had to know to set the quadratic equation equal to 0. So if it's been a while, just be patient with yourself as you review those concepts, okay? And check out all the supplementary materials that we have in the course for algebra review. Okay, moving on. Now we're going to talk about special triangles, and these are two triangles that come up very frequently throughout the course. So one of them is a 30, 60, 90 degree triangle, and the sides are all in a certain ratio with one another. So here's another thing to keep in mind. The smallest side in a triangle is always opposite the smallest angle, and the largest side is opposite the largest angle. So in a 30, 60, 90 triangle, the smallest angle is 30, and the smallest side we're going to represent right now with t, okay? T could be 1, 5, anything. Now, the side opposite the 60 degree angle, the medium-sized one, okay, not the biggest one, the medium-sized one, is always going to equal t times rad 3. And lastly, the side opposite the 90 degree angle is equal to 2 times t. So this only holds in a 30, 60, 90 triangle. Similarly, in a 45, 45, 90, that's an isosceles right triangle. Each of the legs is equal to each other, right? Because you've got two 45 degree angles. So if one leg is t, the other leg is t also. And the hypotenuse is equal to t times rad 2. So these are helpful relationships to memorize because it'll save you some time when you're doing certain computations, and they're going to come up frequently as we continue to study trigonometry throughout the course. Okay, so let's look at a couple applications. A ladder is leaning against a wall, and the top of the ladder is 4 feet above the ground. And the bottom of the ladder makes an angle of 60 degrees with the ground. So start drawing a picture. Don't let all the words overwhelm you. Here is the wall. Here is the ground. And a ladder is leaning against the wall. So here's my ladder. All right, nice little ladder. And the top of the ladder is 4 feet above the ground. Ooh, okay. So that means this distance right here is 4 feet. Let's switch colors up. This is 4 feet. And the bottom of the ladder makes an angle of 60 degrees with the ground. Bam. How long is the ladder and how far from the wall is the bottom of the ladder? Okay, here's a 90-degree angle. That little angle in there is 60 degrees because they told us. That means this angle up top has to be how many degrees? What am I left with? I only have 180 in the triangle. This has to be 30 degrees. So we have a 30, 60, 90 triangle. I'm gonna pop it out here so we can zoom in. So this side is 4, this side is 30 degrees, and this side is 60 degrees. Now remember, T is opposite the smallest side. So opposite 30 is T. And opposite the 90-degree angle is 2T. And opposite the 60-degree angle is T times rad 3. Oh, okay. So that means T times rad 3 is equal to 4. So T rad 3 equals 4. I'm going to solve for T. In order to do that, I need to divide by rad 3. So now we have T equals 4 over rad 3. Now I can't leave my answer like that. I'm not allowed to have a radical in the denominator. So we're going to rationalize. We're going to multiply by rad 3 over rad 3. So now I have that T equals 4 rad 3 over rad 3 times rad 3. That's rad 9, which is 3. Okay, so now I know how far from the wall is the bottom of the ladder. It's 4 rad 3 over 3 feet. That's that part. Now, how long is the ladder? The ladder's length is equal to 2 times T. So 2 times T is going to be 2 times 4 rad 3 over 3. Now you can think of this as 2 over 1. 2 and 4 are not underneath the radical, so they're going to get multiplied by each other. And then you just bring that rad 3 along for the ride, and then in the denominator, I have 3 times 1, which is just 3. Oh, 2 times 4 is 8. Why did I write 4? 2 times 4 is 8. Rad 3 over 3. So it's 8 rad 3 over 3 feet. That's the length of the ladder. And it's 4 rad 3 over 3 feet away from the wall. Okay. Now again, if it's been a while since you worked with radicals or rationalized denominators, we're going to be practicing all of that. So just be patient with yourself. If you've recently taken algebra, then it's probably fresh on your brain. Okay, last example. A 10-foot rope connects the top of a tent pole to the ground. Ooh. If the rope makes an angle of 45 degrees with the ground, find the length of the tent pole. Okay, so here's the tent pole. And a 10-foot rope connects it to the ground. So this is a rope, and it's 10 feet long. And they're telling us the rope makes an angle of 45 degrees with the ground. Find the length of the tent pole. So they want to know what this length is. Well, in this case, I have an isosceles right triangle where each of the legs is equal to t. And then remember the hypotenuse is t rad 2. So t rad 2 is equal to 10 feet. And just like in the last problem, I want to find t, so I'm going to divide by rad 2, divide by rad 2. And we have t equals 10 over rad 2. Now remember, you're not allowed to leave a radical in the denominator, so we got to rationalize. I'm going to multiply by rad 2 over rad 2. And now we have t equals 10 rad 2 over 2. But I can simplify this a wee bit, right? I can cancel out this 2 with the 10. Now this is a 5. So our final answer is going to be 5 rad 2 feet. That's the length of the tent pole. Okay, and that concludes the lesson. Stay tuned. We're going to go over the rectangular coordinate system next. And happy studying.